So we're going to talk about logarithms today. So what are logarithms? We just talked about exponents and exponential functions, and logarithm is very closely related to that. So let's go back and look at this function that we already know. So I'm looking at y equals 2 to the x, and I made a table over here with some x values, and I evaluated it and found the x, y values here, and I plotted those points, and I drew a nice little curve in blue. Okay, so what we notice from here is that the horizontal asymptote of this function is y equals 0. So if you extend it, that's going to be your horizontal asymptote. At no point will your curve go below that or even touch it. And there's no vertical asymptote. Y-intercept is 0, 1. No x-intercept because it's not going to really touch the x-axis. Domain is going to be all real numbers, and range is y is greater than 0. So these are things that we probably already knew before today, right? This is an answer to, okay, what happens if I raise 2 to a certain power? So I could raise it to -2 or like 0th power or second, third, or whatever number that we choose. But what happens if we want to know, if we want to solve 2 to the x is equal to 8, right? So it's a little different because instead of figuring out what this value is based on a given x value, now I'm giving you the answer and I want you to find out what my input was here. So doesn't that sound a lot like inverse functions? Right. So what 2 to the x equals 8 is asking for is, okay, what did you plug in for x to get 8 out, right? And so that's exactly what we did for inverse functions. Remember in the last unit when we talked about trig, we may remember that sine of 30 degrees is 1/2, and inverse sine of 1/2 was 30 degrees, right? So the inverse function took the output of the original function and gave the input out, right? So in this case, if we let f of x equals 2 to the x, we know that f of 3 is 8, and therefore f inverse of 8 is 3. So what we're looking for in this case is a function, the inverse function of y equals 2 to the x. And in our case, that's going to be log base 2 of x. And so that's when the logarithm happens. It comes in. So log is short for logarithm, and this is precisely what we talked about. It's asking, all right, the base is 2, and the answer was x. What did you raise it to? What did you raise to get this answer here? So, okay, this x and that x are not the same. All right, so to make it a little more clear, from our example, 2 to the third power is equal to 8. So we are all familiar with this, and the equivalent statement in logarithm is this. So this says log base 2 of 8 is 3. So this is the output of the log expression is the input in the exponent form, right? In general, you can write it this way, but I mean, to this day, I have this in my head. I don't really mess with the a's and b's because a's and b's can go anywhere, really, right? Even if you switch them around, that's still going to work. Whereas 2 to the third power is equal to 8, I can't really arrange those numbers to make any sense if I change it up, right? So this makes sense to me. I use this to remember the log and exponential equivalence still today. Okay. So here, I also want to talk about the function, what that looks like. So now what I'm going to do, I'm going to pick a different color and plot the inverse function, right? So in this case, I'm going to still look at this table, but my y values are going to be my input and my x values are going to be my output. So what is that going to look like? When x is 1/4, y is -2. When x is 1/2, y is -1. When x is 1, y is 0. When x is 2, y is 1. 4, 2, and then 8, 3. Right, so my graph Just like that. Okay, so this graph, this is the graph of y equals log base 2 of x. Right, so we know a couple of things about it. We know that there's no horizontal asymptote because in this case, the graph will grow forever. It's going to grow very slowly, but it's going to go still grow forever. So no horizontal asymptote. And there's a vertical asymptote actually. And that's x equals 0. Right? There's no y-intercept, but the x-intercept is 1, 0. Right? No y-intercept. And the domain is that x is greater than 0. Range, any real numbers. So you notice the blue curve and the pink curve, they're exact opposite of it in a way that x values and y values have changed. So horizontal asymptote became a vertical asymptote. There was no vertical asymptote. There is no horizontal asymptote in this case. The y-intercept was 0, 1. The x-intercept is 1, 0. And then domain is now the range, and the range is now the domain. And what we also know from this, our knowledge of inverse functions, is that these two graphs are symmetrical over the line y equals x. If you were to draw this line y equals x, it's going to be a mirror image. Symmetrical over y equals x. And that's how you can see from a graph if two graphs are inverses of each other. All right, so going back down here, using the rules that we know. So in general, a to the x power is b means log base a of b is x. So looking at that, and I'm going to also look at the 2 to the third power is 8 is equivalent to log base 2 of 8 is 3. And I want to try these questions. So write an equivalent exponential statement for those 4 questions, and write an equivalent logarithmic statements for the four questions down there. You can pause the videos now and then try them on your own. And when you unpause it, I'll be here going over the questions. Okay, welcome back. So log base 2 of 32 is 5. Is 2 to the 5th power is 32. Would be the equivalent statement. Log base 10 of 1,000 is 3. So 10 to the 3rd power is 1,000. 2 to the negative 2 is 1/4. And 5 to the negative 1/2 is 1 over square root of 5. All right, what about number 2? Write an equivalent logarithmic statement for 4 to the 3rd power is 64. So that's log base 3 of 64 is 4. No. The other way. Base 4 of 64 is 3. Log base 7 of 49 is 2. Log base 2 of 1/2 is negative 1. And log base 10 of 0.01 is negative 2. And there you go. Now let's practice evaluating logarithms. So if you remember, the very, very important statement for today is this. 2 to the 3rd power is 8. This is equivalent to log base 2 of 8 is 3. But I want you to take a look at the right side here. Now, wouldn't it be a lot easier? Because what it's asking here is, if the base is 2, what was the exponent so that you got 8, right? That's what you're asking. So wouldn't it be a lot easier to evaluate this if you made this 8 into a power of 2, right? Instead of 8 there, if you wrote 2 to the 3rd power, right, you're asking, oh, oops, is 3. In the other way, so it's asking 2 to the third. If you change that 8 to the 2 to the third, that statement looks like that. That's so easy, right? So when you try to evaluate logarithms without a calculator, then what you would do is just that. Change the way it's written inside the argument so that the bases are the same. You will get it here. So look at this one. If log base 10 of this is a million, right? So if I change this to log base 10 of 10 to the 6th power, what this is asking is, okay, if the base is 10, what did you raise that power to get 10 to the 6th power? And obviously this is 6, right? You see how easy this is now? Okay, so I'm going to erase this part just a little bit, and I'm going to look at the next question, log base 3 of square root of 3. If I change this to log base 3 of 3 to the 1/2 power, using our log rules or exponent rules, then it'd be just 1/2. So this is when your knowledge of exponents and exponent rules are coming in really handy, right? Number 3, log base 5 of 125. I know that 125 is 5 cubed. So this is log base 5 of 5 cubed. It's 3. You might be asking yourself, well, what if I didn't know that 125 was 5 cubed? What then? Well, tough luck, right? You just go look at some square and cubic numbers and try to recognize them. But 125, you know it's a number that's divisible by 5, so you can divide by 5, and then you get 25, then you would get it there, right? All right, so next one, log base 7 of 1 over square root of 7. So I'm going to change this to log base 7 of, okay, that's 7 to the negative 1/2 power. All right, so that would be negative 1/2. There, okay. And then you might be asked to simplify, but this is very much the same thing, except we don't have numbers and we just have variables. Log base x of x squared would be just 2. Log base m of m cubed would be 3. And this one would be log base k of k to the 1/4 power, so that would just be 1/4. And here, that's log base x of x times x to the 1/2. And so that's log base x of x to the 3/2. So that would be 3 over 2. Solving logarithmic equations is also easy if you remember the equivalent equations or equivalent expressions. So I wrote it down here the way I remember it. So 2 to the 3rd power is 8, and that's the same thing as log base 2 of 8 is 3. Okay, so if I remember that over here, log base 3 of x is 5, so base is 3, exponent is 5, and that's equal to x. So I know that x is equal to 243. So you're going to do the rest of like all 4 questions now, but you should pause the video now and try these on your own and see if you can do them. Okay, we're back, and here we're looking at number 1. Base is 2 and the exponent is 3, so x is equal to 2 to the 3rd power, which is 8. Number 2, x is equal to base is 4, exponent is 1/2, that is 2. Now here it's a little bit different because it's 81 is x to the 4th power. Now normally when you do this, you would take a square root and maybe a square root again or something like that. And either way, x could be 3 or negative 3 if you just look at this equation. X to the 4th is 81. But because this is logarithm, x is going to be positive. So x is 3. All right, and then lastly, 2 to the 3rd power is what's inside x minus 6. And so 8 is x minus 6, and therefore x is. Okay, now the laws of logarithms. So just like we had exponent rules or laws of exponents, we also have laws of logarithms. The first, you need to remember that if f of x is 2 to the x, then f inverse of x is log base 2 of x. And you also need to remember the composite of inverse functions is the identity function. That just means f of f inverse of x is x, and f inverse of f of x is x. So this is something that we've already done before, and in terms of our exponents and logarithm expressions, 2 to the power of log base 2 of x is x, because that's a composite of this and that, and log base 2 of 2 to the x is x. Now this is already something we've done just now, but that's a composite of f inverse and f. Okay, so we're going to use these two properties to prove the laws of logarithms. You don't have to know how to prove them, you just have to know how to use the rules for our class, but proof is going to be a part of the DP course anyway, so you might as well get used to some techniques or maybe how we prove things. So let's say I want to find the law of logarithm involving this expression, the first one here. What would that look like? Well, what I'm going to do is I'm going to have a general base, a log base a. That a value can be any positive number there, and m and n can be any numbers, right? Any positive numbers, right? So how would we prove or figure out the statements, right? We're gonna figure this out. So m and n are just any numbers, but I'm gonna write it. I'm gonna be trying to be clever here, and I'm gonna write it as log base a of m. I'm gonna write it as a to the power of log base a of m times n. I'm gonna write it as a to the power of log base a of n, because I know they're the same things, right? A to the power of log base a of m is m, right? So we're looking at this. I just replaced 2 with a and then m with x, and that would be the same thing, and same thing with n. Then I'm using my log rules to combine these two expressions here, and that's going to be log base a of a to the power of log a to the m plus log a to the n. Because they're exponents, you add them. And if you look at this whole thing, it's going to be log base a of a to the power of this. So it should just be this part. So log base a of m plus log base a of n. So here's the first law. First rule, log base a of m times n is log base a of m plus log base a of n. So that's our first property. All right, second, if it's a division, what do we do? Well, doing something very similar here. So I'm going to write m as a to the power of log base a of m, and n, I'm going to write it as a to the power of log base a of n. And then using our properties of exponents, I'm going to write it as log base a of a to the power of log base a to the m minus log base a to the n. And the same reason as before, it's just going to be log base a to the m minus log base a to the n. So what we see is that log base a of m over n is going to be log base a of m minus log base a of n. Okay, and it's important here at this point to note that m and n have to be, so here m and n are positive numbers. A is also positive, but a is also not 1. there. And for the last proof here, b is also positive here. B has to be positive as well. Okay, and here I'm going to write b as a to the power of log base a of b. And then it's b raised to the mth power, so it's going to look like that. And using the exponent rules, I'm going to multiply the exponents because it's raised by m. So I can write log base a of a to the m times log base a of b. And again, that's just m times log base a of b. So what we notice is that if there is an exponent, no, that's not what I meant to do there. If there's an exponent, it just comes down in front and gets multiplied. So those are my three log rules or laws of logarithm. So let's use that to solve some problems. I have 8 problems that I'm going to do together, and your task is to write these as a single logarithm. And I highly recommend that you pause the video now and try these on your own and check your answers by replaying the video. Okay, welcome back. Something that you probably noticed is that these are missing here. I'm not sure if I mentioned before, but if we don't write any base there, it's base 10. So if something's missing, so log of x, that's the same thing as log base 10 of x. Okay, so let's do these problems. I'm going to use my log rules, and that'll be the first rule here. Log base a of m plus log base a of n would be log base a of m times n. Right? So I'm going to use that rule and write this as a single logarithm. A times 2, which is log base 10 of 16. And when I need to, I will write the base. If it's anything other than 2 or e, but we have a special symbol for log base e, and we'll talk about that later. And here I'm using the same rule, log base 2 of 4 times 5 be log base 2 of 20, and 20 is not 2 to the power of anything, so any clean number, so we're just going to leave it at that. And here we're using the second rule. Remember, when there's a subtraction there, it's division inside the log. So it's log base 2 of 40 divided by 5, which is log base 2 of 8. In this case, I can write this as an integer, 3. Okay. Number 4, log base 10 of 5 and log base 10 of 4. You add them together, that would be multiplying, and then you are going to subtract log base 10 of 2, so you would divide by 2 at the end. You can do it all at once, or you can do it one at a time. And you get log base 10 of 5 times 4 over 2, which is log base 10 of 10, and that'll just be 1. Remember that even there's nothing there, it's just 10. Okay, and lastly, this is like, not last, number 5. This is where people make mistakes sometimes when you have like a minus and a minus. So this is log base 3 of 6 over 2 times 3. And the reason it's like that is that you can write this as that, right? So this makes sense that you would multiply 2 and 3 and then divide by it, and that would be log base 3 of 1. And okay, think about it. 3 to the what power gives you 1? And that would be 0. Okay, and here is a mix of the first rule and the last rule that we proved. I'm going to first write the first expression as log base 10 of 2 to the 5th and plus log base 3, or log base 10 of 3, and that would be log base 10 of 2 to the 5th times 3, and that would be, this one's 32, so it's log base 10 of 96. Right, 32 times 3, yeah, it's 96. And the next one, the same deal. 1/2 becomes the exponent, so log base 6 of 4 to the 1/2 times 3. Right, that's going to be log base 6 of 6, which is 1. Yeah, so something that we need to remember is that if these numbers are different, then you can't use the rules. They have to be the same base. All right, so having said that, there is a 1 there, which doesn't fit with the rest. So what I'm going to do is similar to what we figured out here, up here on number 4. 1 can be written as log base 10 of 10 or log base b of b or anything like that. In this case, the rest of them are log base 10s, so I'm going to write 1 as log base 10 of 10. And the second expression, 3 log base 10 of 2, is going to be log base 10 of 2 cubed plus log base 10 of 20. So it's going to be log base 10 of 10 divided by 8 times 20. Right? And that would be, I'm going to need, okay, that's going to be 2 times 2 times 2. And then 4 is going to go over here, and 2 is going to go over there, and I'll have 25 left. Log base 10 of 25. And I can't simplify that any further.